In this video, we will further examine the graphs of polynomial functions. A polynomial function we saw previously is a function of the form f of x is equal to a sub n x to the n, and so on and so forth until we get down to the constant. So we have all of these terms where the powers, the exponents on x are whole numbers, and the coefficients will all be real numbers, with specifically this leading coefficient a sub n not being 0. We call it a polynomial function of degree n in this case. Now, we looked at end behavior of polynomial functions before, but I will add that when we have the graph of a polynomial function, the graphs of polynomial functions are always continuous. Polynomial functions don't have any sharp corners. The domain is all real numbers. Each polynomial function will have one y-intercept and at most n x-intercepts. That n is the polynomial function of degree n will have at most n x-intercepts. And at most n minus 1 turning points. That's where the graph can turn from increasing to decreasing or from decreasing to increasing. And we saw earlier that the end behavior of a polynomial function is that as the x value goes to infinity, the corresponding y value will either go to a positive or negative infinity. The same is true as x gets smaller. As x goes to negative infinity, the end behavior is going to either go to positive or negative infinity. So these are really nice features of polynomial functions and their graphs. We have the fact that it's continuous, and it's continuous over the entire domain of all real numbers. We know at most how many x-intercepts we have. If it's a polynomial function of degree 2, then it has at most 2 x-intercepts. If it's a polynomial function of degree 3, it has at most 3 x-intercepts. I am saying at most here, it could have less. And the same thing with turning points. We have one lower than that as far as turning points go. Again, that's places where we go from increasing to decreasing. So that's what we mean. Turning points, here I've defined it. That a turning point is a point where the function turns from increasing to decreasing or vice versa. I want you to make sure you have that written down. Remember, we said that the end behavior of a polynomial function is the same as the end behavior of the function whose just has the lead term. Let's take a look at a couple of different polynomial functions. We have f of x is equal to x squared minus 2x minus 3, and g of x is equal to x squared plus 2x plus 10. We'll graph both of these on Desmos. Here's the graph in red of f of x is equal to x squared minus 2x minus 3. We can see that it is continuous. There's no place where there's a jump in the graph. So we can draw it in a single motion without lifting our pen. As we can see, this is a polynomial function of degree 2. because our lead term there is x squared. And you'll notice in this case, we have actually two x-intercepts. As always, we have one y-intercept. And there's no sharp corners. Now, by sharp corners, what we're talking about is like an absolute value corner. Here we have a smooth corner. So we can draw it like this. It doesn't have a sharp straight line meeting another straight line. So this is the graph of f of x. Again, continuous. This one has two x-intercepts and one y-intercept. Now the graph of the g of x is the graph here. It is also continuous. It also doesn't have a sharp corner. It also has one y-intercept. But in this case, it doesn't cross the x-axis. So this one has 0 x-intercepts. That's what we mean by at most at most two x-intercepts. It could be 2, it could be 1, it could be 0. By the way, I didn't mention this on the previous, but the vertex is the point at which this graph turns from decreasing to increasing. So the vertex of this parabola is the turning point of this parabola. And there's only one of those. The same is true on my previous function. We had one turning point, and that was at the vertex. That goes from decreasing. At that point, it switches from decreasing to increasing. So that's the turning point of the parabola. Here's another example of two functions. These are two cubic functions. F of x is equal to x to the third minus x squared minus 2x minus 3. And g of x is equal to negative x to the third minus 2x squared minus 2. We'll graph both of these using technology as well. I will graph them on Desmos, but you can graph them on a TI-84 calculator or another graphing calculator if you'd like. In this case, I have graphed f of x. Here it is graphed in red. You can see that obviously the end behavior, as we move to the right, it goes off to positive infinity. As we move to the left, it goes to negative. We can also see that it's continuous. This one only has one x-intercept at this point here, but it has two turning points. One at the top here where we change from increasing to decreasing, and then one down here where we change from decreasing to increasing. So we have two turning points, and that makes sense because this is a function of degree 3. So we can have at most two turning points. Obviously, in this case, we have one y-intercept. There it is at 0, negative 3. This one only had one x-intercept, but you can imagine that if we moved this up, you could imagine shifting this thing up and ending up with 3 x-intercepts. We obviously didn't have that. We only ended up with one x-intercept. So continuous, no sharp corners, one y-intercept, at most 3 x-intercepts. In this case, we get 1. And you can see the end behavior. With g of x, we have negative x to the third minus 2x squared minus 2. Again, we have one x-intercept, couple of turning points. It's continuous. And in this case, notice the end behavior does the opposite because we have a negative x to the third. So as you move to the left, the graph shoots off to positive infinity. As you move to the right, the graph shoots down to negative infinity. So these are really nice features of polynomial functions. If I know my function is a polynomial function, I know it's going to have these really nice features. Obviously, x-intercepts are another feature of polynomial functions. Again, we can have at most n x-intercepts. And if we want to actually find the x-intercepts algebraically, we know how to do that, or we should know how to do that. We set the y value equal to 0, and we try to solve the polynomial equation. It'll be an equation once we set y equals to 0, y equal to 0. The x-intercepts are synonymous with a 0 of a function. The x-intercepts are the point a comma 0. So when you plug in a into the function, you get a 0. That is called a 0 of the function. So we say that the number a is a 0 of the function if, when I plug it in, I get a 0. In other words, every 0 of the function, every real number 0 of the function gives me an x-intercept. Now, we'll look at how to find x-intercepts and how to find zeros of a polynomial function a lot in the next couple of sections. We know to find an x-intercept, we set y to 0 and then solve. Right now, we'll take a look at one type of method for finding these x-intercepts, for solving the polynomial functions. And then later on, we'll see some other methods. Maybe in other videos, we'll see other methods. The method that we're going to focus on right now is factoring. We've factored quadratics in a previous video. Factoring higher degree polynomials will not work exactly the same, but we can try to factor some. Again, if factoring doesn't work on a polynomial, then we'll look at some other tools to use in later videos. But in this video, we're just going to find x-intercepts through the method of factoring. So let's take a couple of examples which are already factored for us. And let's ask if we can find the x-intercepts of these two functions. If you want, push pause on the video and figure that out. Otherwise, I will do these in a couple of seconds. So we set y equal to 0, the output value equal to 0. And the nice thing about these two cases is that we're already factored. And therefore, all I have to do is say that if I have a bunch of numbers multiplying to give me 0, then one of those numbers would have to be equal to 0. So either 0 is equal to 3, or 0 is equal to x minus 2. I'm going to rewrite that as x minus 2 is equal to 0. Or x minus 4 is equal to 0. Or x plus 5 is equal to 0. Now, the 0 cannot be equal to 3. So this one, we're going to cancel out. That can't actually happen. So I just say that doesn't work. That leads me to a dead end. But the other three equations could happen when x are various values. So in the first one, x minus 2 is equal to 0 when x is equal to 2. In the second one, x minus 4 is equal to 0 when x is equal to 4. In the third one that's left, x plus 5 is equal to 0 when x is equal to negative 5. So this leads to 3 x-intercepts. Those are all real numbers. Therefore, I have 3 x-intercepts, one at the point 2, 0, another at the point 4, 0, and another at the point negative 5, 0. So we have 3 x-intercepts. And by the way, we'd have 3 zeros as well. These 3 numerical values are all zeros of my polynomial function. In the next example, we have a number of things we can set equal to 0. So, well, let me start out by saying that in order to find the x-intercepts or the zeros of this function, we'd set each piece equal to 0. So either negative x is equal to 0 or x minus 7 is equal to 0. Technically, we'd have another x minus 7 is equal to 0 because we have 2 copies of x minus 7 here. But that's going to lead to the same solution. So I don't need to write both copies there. So x minus 7 is equal to 0. X plus 1 could be equal to 0. Forgot to put the word or x plus 5 is equal to 0. This gives me 4 different values that are zeros of my function. 0, 7, negative 1, and negative 5 are all zeros of my function when I solve each equation. That means the graph of this g of x is going to have 4 x-intercepts, one of which is going to be 0, 0, or the origin. The other is going to be 7, 0. The other is going to be negative 1, 0. And then lastly, we'll get negative 5, 0. This shows that g of x is going to have 4 x-intercepts. It's going to hit the x-axis at 4 different points. If you multiplied out g of x, the degree of this would be 7, and we ended up with 4 x-intercepts. This would be a degree 7 polynomial if you multiplied it out. A lot of times people will say the 0 of 7 has multiplicity 2 because the factor of x minus 7 showed up twice. And the 0 of negative 5 has multiplicity 3 because the factor of x plus 5 showed up 3 times. Negative 1 would have multiplicity 1 because that factor just showed up once. 0 has multiplicity 1 because that factor just showed up once. In my previous function, this would have been a degree 3 function if I'd have multiplied it out. And we can see we end up with 3 x-intercepts. So we can see that in this example, we found the x-intercepts quite quickly because it was already, each of these were already factored for us. Therefore, when we set one side equal to 0, all we had to do was set each linear factor equal to 0 and see what happens. What if we have a higher degree polynomial, higher than a quadratic, and we want to find x-intercepts of functions like these? We're going to look at a couple of factoring tricks. This is not going to be a complete look at all of the properties of factoring that we can do, but rather we'll just see a couple of tricks of factoring in this example, and then also when we get to example 5. Here we have f of x is equal to x to the third plus 6x squared plus x. And you can see g of x is equal to negative x to the third plus 2x squared plus 35x. Let's go ahead and factor these two. If you already know how to do it, push pause on the video and then try that on your own. Otherwise, in a couple of seconds, I will factor these two polynomial functions. All right, so to find the x-intercepts, we set our y value equal to 0, and then we have to factor. And that means I have to factor this right-hand side polynomial. The first trick that we'll do is we'll factor out a greatest common factor. In this case, that's going to be x. Each individual term has an x in it, so we can factor out the value of x, and that's going to give us x squared plus 6x plus 8 inside of the parentheses. Once I do that, then I can look at this quadratic inside of the parentheses and factor that. X squared plus 6x plus 8. Well, I can factor that into x plus 2 times x plus 4. I look for factors of 8, which add to 6. Those factors are 2 and 4. And so what would happen is I'd have 0 is equal to x, and then the inside of the parentheses factors into x plus 2 multiplied times x plus 4. And now we are at the place that we were earlier. And we can say, well, that means x has to be 0, or x plus 2 has to be 0, or x plus 4 has to be equal to 0. This gives me 3 solutions for this equation. which gives me 3 zeros or 3 x-intercepts. Here, all of my solutions are real numbers. X equals 0, x equals -2, x equals -4. Those are my 3 zeros, and my 3 x-intercepts are just corresponding points. 0, 0, -2, 0, and -4, 0. So those are the 3 x-intercepts of f of x. If you want to try to do that same thing with g of x on your own, you can push pause on the video. I will go ahead and find the x-intercepts of g of x right now. I would set the y value equal to 0. In this case, you'll notice that I have a -1 as my coefficient of x to the third. Also, each term on the right has a factor of x. Those two features combined means that I should factor out a -x so that when I factor out a -x, that'll leave me an x squared with this term. Again, I'm dividing each term by -x, so I get x squared. Then I'd get a -2x. Again, divide 2x squared by -x. And then divide 35x by -x, you'd get a -35. Again, I have something multiplied times a quadratic, which has a 1 in front of the squared term. I can factor that quadratic into 2 linear pieces. Factors of -35 that add to -2 will be -7 and +5. So I would get x minus 7 and x plus 5 in my factorization. Now we can say each piece can be set to 0, each linear piece. So x, -x is set to 0, x minus 7 is set to 0, and x plus 5 is set to 0. That gives me 3 solutions. X is equal to 0, x is equal to +7, and x is equal to -5. Those 3 solutions are all zeros of g of x. The x-intercepts are 0, 0, 7, 0, and -5, 0. So one trick we can use if all of the terms have an x in it is just to factor out that x. And then factor out the coefficient on whatever the highest term is. So factor out the lead coefficient as well. And hopefully you get something that is easy to factor on the inside of this parentheses. So that's one tool for finding x-intercepts using factoring out the greatest common factor. Now we can't always factor out the greatest common factor. In fact, sometimes when we factor out the greatest common factor, we'll have a cubic or we'll have something else. So let's look at another tool that we can use in terms of factoring. This tool is only going to be able to be used in special cases, but still I can use it in these two cases. So we'll look at another tool for factoring right now. We're going to find the x-intercepts of these two functions, and we'll factor the polynomials on the right, and in the process, we'll see this new tool. Here's our function. We want to set that function equal to 0. The output of that function equal to 0. Doesn't matter if you put equal to 0 on the right or the left. In the last couple examples, I put that on the left. If you feel more comfortable putting that on the right, go ahead and put the equal to 0 on the right. Doesn't matter which side of the equation we're going to use. Now, here's the trick in this case. What I do is sometimes I can pair the first two terms and the second two terms. This is not always the case. And if I compare the first two terms and the second two terms, and then also factor out the greatest common factor of each. So in this pair, I'd factor out an x squared. I'd get x squared times x plus 7. In the second pair, I'd factor out a negative 3. And if I factor out a negative 3 in the second pair, I also get x plus 7. Notice that when I factored out what was left after I factored out the x squared is the same as what was left when I factored out the negative 3. So this is like saying x squared times a minus 3 times a. Well, I could factor out an a in that case. Think about it like this: x squared times a minus 3 times a could have been rewritten as x squared minus 3, and I distribute the a. Well, the a here is just the x plus 7. So this entire expression can be rewritten as x squared minus 3 multiplied times the quantity x plus 7. The right-hand side stays equal to 0. And now I can solve this. If I wanted to try to factor this quadratic, I could, but I think it's easier just to solve and say x squared minus 3 is equal to 0, or x plus 7 is equal to 0. In the first case, when I add 3 to both sides, I get x squared is equal to a positive 3. In the second equation, if I subtract 7, I get x is equal to negative 7. I still have an x squared here, so what I would do is I take a square root of both sides. Make sure when you do that, you take the positive and the negative square root of 3. So this first equation becomes x is equal to the positive square root of 3, or x is equal to the negative of the square root of 3. And then the second equation is just solved. It's x equals -7. So here are my 3 zeros for this polynomial function. If you were to plug in a square root of 3, you'd get a 0. If you were to plug in a negative square root of 3, you'd get a 0. And if you were to plug in a -7, you would get a 0. That means there are 3 x-intercepts, one of which is the square root of 3, 0. The other is negative square root of 3, 0. And the last is -7, 0. So this trick about matching up pairs of terms and then factoring out the greatest common factor of each pair is a nice trick when it works. Doesn't always work, but in this case it did. Let's take a look at the next function, g of x. And let's set the output there equal to 0 in order to find my x-intercepts. I'll put the 0 on the right-hand side in this case. Doesn't matter if you put the 0 on the left or on the right-hand side. Now, this one is going to be a combination of the two tools that we used earlier. So basically, what I would do is I would do the pairing. You could do the pairing first, or you could factor out a greatest common factor from all 5 terms or not 5, all 4 terms first. It doesn't matter which way you do it. I think what I'll do is I'll take the greatest common factor of this pair and then the greatest common factor of this pair. You know what? No, let's do the reverse. Let's actually factor out a greatest common factor of all 4 before I get started. So all 4 terms have a common factor of x squared. Let's factor that out before I get started. This will leave me 2x to the third minus 9x squared plus 10x minus 45. Right-hand side of the equation is still equal to 0. And then what I'll do is I'll factor the thing inside of this parentheses. And in order to factor this thing, now I'll do the pairing up. I have to be very careful when I do this so that I have the right parentheses notation. Because when I factor out the greatest common factor here, I'm just going to be factoring out an x squared. I'll be left with 2x minus 9. When I factor out a greatest common factor between 10x and minus 45, it will be a positive 5. And I'll be left with 2x minus 9. Just like before, since 2x minus 9 matches up with 2x minus 9 over here, the x squared plus 5, this x squared and this plus 5 can all be multiplied times 2x minus 9. Here's where it gets tricky. Don't try to throw in this x squared. This x squared is in front of the entire bigger parentheses. So we're going to get x squared. Maybe I'll put this in brackets. And then inside, I'll have x squared plus 5 multiplied times 2x minus 9. And that's all set equal to 0. Now the extra square brackets don't do me much good. We have x squared times x squared plus 5 times 2x minus 9. All set equal to 0. And I can set each one of those pieces equal to 0. So x squared, I'd set equal to 0. X squared plus 5, I'd set equal to 0. And then 2x minus 9, I'd set equal to 0. Let me clean that up a little bit. So x squared could be 0. X squared could be equal to negative 5. Or x squared, not x squared, 2x could be equal to 9. Now, let me cancel that. Excuse me. I get a couple of different solutions, but 2 of those are going to be imaginary number solutions. So the first, when I take the square root of 0, you get 0. Plus 0 and minus 0 are the same thing. So the first equation yields x equals 0. The second equation yields x is equal to the positive square root of 5 times I, or the negative square root of 5 times I. I'm going to put I in the front there so it's easier to see. And then the last equation gives me an x value of 4.5. So here are all of the zeros of this function. 2 of the zeros of this function are imaginary, so they are not going to be where we cross the x-axis. Therefore, if I'm looking for the x-intercepts, I only have 2 x-intercepts, one at the point 0, 0, and the other at the point 4.5, 0. Again, these imaginary solutions do not yield x-intercepts. So there we go. We get 2 x-intercepts out of this polynomial function of degree 5. Now, many times we cannot find x-intercepts by factoring. We're going to look at some other methods later on for finding x-intercepts without using factoring. But in this section, we'll look at one other option. We'll find sort of a range of x values for where the x-intercepts are close. So we're going to say something like, I know there's an x-intercept somewhere between 4 and 5, but I don't know what exact value it's at. Or I know there is an x-intercept between 4.2 and 4.3, but I'm not exactly sure where that number is. So we can approximate x-intercepts if we can't factor. The way we do that is we use the idea of what's called the intermediate value theorem. And basically, here's how the idea goes. Polynomials are continuous. The graphs of polynomials are continuous. So if we have two values on the x-axis, we'll call them a and b, then f of b will give me some output value, f of a will give me some output value. Since a polynomial is continuous, then every value between f of b and f of a should be obtained on the interval between a and b. Hopefully that makes sense. Let me graph it out and it should make sense. So imagine that I don't know what the graph of my function looks like, but imagine that I know that it goes through the point 5, 1 and also through the point 7, -2. Since our function of a polynomial function is continuous, it's going to have to travel, and I'm going to have to draw some sort of shape without lifting my pen that goes from 5, 1 to the point 7, -2. And I can't contradict the vertical line test, so I always have to be able to move right when I do that. So in other words, I can't do this. That would be cheating and that would fail the vertical line test of a function. So I have to go from 5, 1 to 7, 2. Now I can go up a little bit. I can go down a little bit. I can come back up. I can do a lot of different things, but notice that every y value between 1 and -2 is going to be touched by that function somewhere. And the one that we're concerned with in terms of the x-intercepts is the y value of 0. Therefore, if I know that my function goes through the point 5, 1 and my function goes through the point 7, -2, I know there's going to be some x-intercept somewhere between an x value of 5 and an x value of 7. It might be at 6.5. It might be at 5.1. It might be at 6.8. It might be at 6. But it's going to be somewhere between 5 and 7 where we have to cross this x-axis. And it may cross at multiple places. You could cross the x-axis at more than one place, but it has to cross there at least once. So that's the idea behind the intermediate value theorem, that every y value between f of a and f of b should be obtained somewhere on the closed interval between a and b. This is how the intermediate value theorem is actually stated. It says, given two numbers a and b in the domain of a continuous function on a closed interval from a to b. If we have that these two values are not the same, if we have different y value output values, then the function takes on every value between f of b and f of a on the interval from a to b. And in particular, if one of our outputs is positive and one of our outputs is negative, then we know we're going to cross the x-axis somewhere between a and b. So that's the intermediate value theorem. This works for all continuous functions, but now we know that polynomial functions are continuous functions. So the intermediate value theorem will work on polynomials for any a and any b we choose. Now we can do this more generally. So let's imagine we have a function that is continuous, and I know when I plug in a 2, I get a 14. When I plug in a 5, I get a 39. Is there a number somewhere between 2 and 5? Is there an x value somewhere between 2 and 5 that has to have the output value of 22? In this case, we'd say yes, because 22 is between 14 and 39, and we know every value between 14 and 39 is going to exist on the closed interval between 2 and 5. So there is some x value between 2 and 5, which is going to give me out an output of 22. On the other hand, if somebody says, is there an x value between 0 and 2 that gives f of x equals 22? You would say, well, we don't know. The intermediate value theorem does not guarantee that there's a number between 0 and 2. It only guarantees that there's a number between 2 and 5 that hits 22. So if we said, is there a number between 0 and 2 that hits 22? You'd say there may be, but there may also not be. It's not guaranteed by the intermediate value theorem. If I know that plugging in 7 gives me a -2 and plugging in 8 gives me an 11, is there a number somewhere between 7 and 8? Is there an x value somewhere between 7 and 8 that passes through the x-axis? So that's a 0. You'd say yes, because when you plug in 7, you get a negative value. When you plug in 8, you get a positive value. Therefore, somewhere between 7 and 8, we have to cross over the x-axis. We have to have an output of 0. The next question says, is there a number between 7 and 8? Is there an x value between 7 and 8 that gives an output of -5? We'd say, well, again, maybe there is, maybe there's not, but it is not guaranteed by the intermediate value theorem. Our output values, every output value between -2 and 11 has to be reached. -5 is outside of that range, so it may not be reached. It may not be touched. So in the first case, the output value of 0 is guaranteed. In the second case, the output value of -5 is not guaranteed. So we could do problems like this. Let's look at example 8. Example 8 starts with a polynomial function, and it asks, can we find an x-intercept between an x value of 0 and an x value of 2? And then could we get a very close estimate? So what we would do is we would start out by plugging in 0 into my function. I'll go ahead and do that in my head. 0 to the third minus 2 times 0 plus 0 minus 1 gives me a minus 1. And then I would plug in 2 into the function. 2 to the third power minus 2 times 2 plus 2 minus 1 gives me out a value of 5. Again, I am getting that by just plugging that 2 in to my polynomial function. This means that somewhere between the x value of 0 and somewhere between the x value of 2, every number between -1 and 5 is hit. And in particular, there will be a number that's between 0 and 1 that is a 0 of the function. So we will cross over the x-axis. There will be some number that when you plug that number in, I'll call it, I guess, z, you get out a 0. And so there will be an x-intercept. And there might be more. So there will be at least one x-intercept between x equals 0 and x equals 2. Now, the question only asks me, will there be one? So yes, there will be one. There may be more, but there'll be at least one x-intercept between 0 and 2. Now, how could we get a close estimate? Well, what I would do is I'd say, well, I know there's going to be an x-intercept between 0 and 2. Let's pick a number between 0 and 2 and plug it in. The obvious choice here is the number 1. If I plug in the number 1, I get out a -1. So not only do so that's a negative. Notice that when I plugged in a 0, I also got a negative. When I plugged in a 2, I got a positive. Therefore, I'll just use that positive number and say, now I can be more specific. Not only will there be an x-intercept between 0 and 2, now I know that there will be an x-intercept between the x value of 1 and 2. If I wanted to get even closer, what I would do is I would plug in 1.5. That's halfway between 1 and 2. And that is into my original function here. So I take 1.5 cubed minus 2 times 1.5 plus 1.5 and then minus 1. And when I do that, I would get a 0.875 as the output value. That is positive. F of 1 is negative. So I'd say, well, I know f of f of 1 gives me out a -1. I know f of 1.5 gives me out a positive number. So I know that there's going to be at least one x-intercept, not just between 1 and 2, but between 1 and 1.5. And then you could do this by plugging in, you could do this and again and again by plugging in like 1.25 on the next step and seeing what that gives you. And it's going to be either negative or positive or zero. If it's zero, I know it's the zero. If it's negative, then I know between 1.25 and 1.5, there's a zero. If it's positive, then I know between 1 and 1.25 is going to be zero. So I can just keep doing this where I pick any number in between here. I keep picking the middle number, but if you wanted to pick 1.1 as well, or 1.3, or 1. Anything between 1 and 1.5, that's fine too. So you could get better and better approximations by going through that process. And so by going through this process, we can get better and better approximations, and we'll know where our x-intercept will have to land. We know it's somewhere between 0 and 2, and then we've narrowed it down. Now we know it's going to be somewhere between 1 and 1.5. So that is one way of getting approximations for your x-intercepts. Now that way can oftentimes take a long time. It can, to get really good approximations, takes a lot of plugging in and calculating and doing that process over and over and over again. So it's not the most elegant of ways of finding x-intercepts, but it is a way that we can get decent approximations. And you can program a computer to do that in a pretty fast way. Although for a human, it takes a little bit of time and energy. So that's the end of this video on graphs of polynomial functions. We were looking at polynomial functions and then using some of the features on their graphs. Again, the two tools we looked at to find x-intercepts were factoring and the approximating using the intermediate value theorem. We'll see some other tools to find x-intercepts in later videos.